Okay, I'm very happy to have Catherine from our UC Berkeley to tell us something about the homological mirror symmetry for theta devices. Thanks, Catherine.
Thanks so much for your patience. This is joint work with my collaborators, Haniya Azam and Berkeley, and Chiu-Chu Melissa Liu. So I wanted to say a word about symplectic geometry to kind of encapsulate what it is. The definition of a symplectic manifold is a smooth manifold that includes non-degenerate two-form omega, which we call the symplectic form. That means necessarily this is even dimensional. A symplectomorphism, so in the category of symplectic manifolds, a symplectomorphism is a diffeomorphism that preserves the symplectic. Some examples: an scalar manifold, it's scalar form. Phase space, so locally symplectic manifolds like this R2 and J, QJ is a position and PJ is. Some properties of symplectic manifolds are Farman-Kounon squeezing, which says that you can't symplectically squeeze volume. So if you have a symplectic embedding from a sphere into a cylinder, the cylinder needs to be at least as the radius little r of the cylinder is greater than or equal to the radius big R of the sphere. And also, we'll always have a almost complex structure. So the symplectic manifold has, you have the symplectic form omega, you always have a Riemannian metric on the smooth manifold, and the almost complex structure J contains two. In fact, any two determine the third. So a symplectic manifold with omega, your metric G, you have an almost complex structure, which means on the tangent bundle, it squares two digits. Now, the Fukaya category, and my talk is about homological mirror symmetry. Mirror symmetry has a lot of different formulations, and one of them is an algebraic formulation between two categories. And the category on the symplectic side is called the Fukaya category. Objects are half-dimensional submanifolds such that the omega is 0. And morphisms, arrows between two objects in this category, are intersection points. In fact, it's a homology theory called Frantian intersection, Flirt homology, HF. So an example is if you take a slope k curve, slope k line on the two torus with dx, y, dy, so your two torus has area 1. Slope k curve, so here's slope 0, slope 1, slope 2 wraps them twice on the two torus. Then omega is a 2 form, so if you restrict it to something one dimensional, you're going to get 0. So any curve is Lagrangian. And the intersection points between slope k1 and slope k2 is actually the number of intersection points by definition, which is actually k2 minus k1. So like slope 1 and slope 0, 1 minus 0 is 1. So you have this one intersection point here. 2 minus 1, still we have one intersection point between them. But the blue and the red, slope 2 minus slope 0 is 2. So you have one intersection point here, and then you have another one, which is the same as here. So you have opposite sides. Another example is take this in a fiber.
So just making sure, so K2 assuming bigger than K1?
Well, this should be absolutely valid.
Okay.
Yeah. If K2 is less than K1, then you get the degree of this is in degree 1. And if K, so it's absolute value. And if K1 is bigger, if K2 is bigger than K1, then you get this in degree 0. But either way, it's absolute value in difference in the integers. Another way, yeah. Yeah, the K's have to be integers. If they're not integers, you also have notion of, so this is mirror to degree K line bundles, but you also have vector bundles. And there's a corresponding notion of Lagrangian on the side of equip it with what's called the bundle system. So we can also take a vibration. Say take T2 as a fiber, take your base to BC, take slow K Lagrangians as a fiber, and then parallel transport that around a curve. So then your Lagrangian is slow K times an arc in the base. So the conjecture in Kontsevich made in 1994 International Congress of Mathematics was that symplectic manifolds Y compare with the complex manifold X, so that the bounded derived category choose on X is equivalent as categories to the bounded derived category of the Bukai category of symplectic. So this is the homological version. And I'd like to talk about how we find this X next. So here's intuition. Straight through. Say to get your job interviews with the dean, and they want to how's your work teacher to it's related to this. So the idea is, my understanding is string theory would be a way to unite physics, small things, quantum mechanics with gravity at large scales. And the idea is that quarks would be actually made up of these strings vibrating. And in order for the theory to work, they have to move in 10 dimensions. And this 6-dimensional Calabi-Yau, for the 6 extra dimensions, that's the thing that has a mirror from the physics perspective of T-duality. So T-duality gives 2 different Calabi-Yaus with the same partition function. So that's when you integrate over all states of the string, where a state is a sigma model. So a Riemann surface like S1 times R. So I think about it as like S1 times T is where the string is at time T. And then as you move along the cylinder, that's the string moving in Y. And so you integrate over the energy over all of these sigma. And there's 2 different manifolds that give the same number when you do that integral, called the T-dual. And Strominger, Yau, and Zaslow formulated mirror symmetry as this T-duality. And the idea is you need a Lagrangian torus vibration. In order to do this process, you need a Lagrangian torus vibration in order to get the SYZ mirror. Then once you do that, you have the same base and your dual fiber. So if you have a torus fiber and you want to say, well, what's the dual fiber on the mirror? It's actually the space of flat connections on the trivial line bundle of the original fiber. Essentially, it's the holonomy. What is the e to the I theta, the holonomy that you multiply by when you go around the loops on the original fiber? So just a quick motivation of why it should be symplectic and complex geometry that are mirror. So this process, geometrically, what you're doing is you're inverting the radius of a fiber. So if you have T2, you have R1 is the length in the base and R2 is the length. R1 is the length in the fiber and R2 is the length in the base. Symplectically, a 2 form in 2 dimensions, it captures the area. So we can just write down what the area would be, R1 times R2. And the complex structure, what you multiply by to go by 90 degrees is R2 divided by R1. So if you have, length R1, R2, then the number you have to multiply by to get from length R1 to R2 is R2 divided by R1. And if you take the T-dual, so you invert this fiber here, now the symplectic area is what is R2 divided by R1 multiplying these 2. And the complex structure is now R1 times R2. So symplectic area here is the complex lattice that you quotient by in the 2 torus here. And also the complex structure of this is mirrored to the symplectic structure of this. So hopefully that provides just kind of like a rough idea of intuition why symplectic and complex geometry should be mirror.
Another thing is to tell the beam is that just conjecture. Well, today we understand it as relating categories of D-branes in physics language, but the time of the ICM when he actually gave his conjecture was before D-branes were discovered in string theory. And discovery of D-branes, like one of the most important discoveries in string theory. So it's a time when mathematics predated it.
Oh, I see. Okay, that's good. Good motivation for why we care about the math part of it. Okay. So speaking of branes, let's look at T2. What are the objects? The Fukaya category, so we're taking this as the symplectic form, is the omega, and we're defining a variable tau, which is I times omega. Lagrangians we saw are slope k lines, and we allowed two more numbers. One is the amount b, so like this line here goes through 0, but we could also say this one is slope 1 that wraps around here. We also allow what we call L infinity, so these vertical Lagrangians. So this is one that's at r equals -1 here, so -1. So the b is a shift, and we allow another real number, which is a. So that's the holonomy e to the ia of the flat connection on this Lagrangian. On the other side, for the branes, we have, so the mirror is now z, the lattice is 1 in the real direction, and then I times omega, where omega is this area in the complex direction. And the branes are we look at the line bundles L, where L is defined to be degree 1. It's an ample line bundle on the 2 torus. And so you define it as a copy of C that has the correct periodicity condition to descend to this 2 torus. So we have the area omega is mirrored to the lattice omega. We have Lagrangians of slope k and shift b, connection form A. We package A and B together into a complex number Z. So the branes are L hat with slope k and complex number Z. So part of the complex numbers is shift B, and the other part is this connection 1 form. On the mirror side, we have degree k line bundles that are mirrored to slope k Lagrangians, and we allow a shifting by an amount of the same number Z. So the mirror brane here is shift by Z of a degree k line bundle. And for the mirror morphisms, we have intersection points on the Fukaya category side. We have sections of these degree k line bundles, which if you pull it back to C, that's just going to be periodic functions, which have a Fourier series expansion. So we can write down concretely what they are. They're the theta functions. And their 0 set is theta divisor, which is the title of the talk, mirror symmetry for those. Yeah. This is a number, because if, let's say we didn't have Z, let's say we just had theta equals minus KR. Well, there's a lot of degree K line bundles. And we'd like to say that we know what the mirror of all the degree K line bundles are. There's a Picard zeros worth, like a 2 torus worths of line bundles of degree K by translating by this Z, pulling back by translation. So the mirror to that is you take the like tau real part, and that goes into a connection 1 form, and then the tau imaginary part, this B, goes into a shift. So it kind of splits into 2 parts. That's why we need the Z on this side.
Can you explain how you get, how do I see the data function? In this picture, right, the final event intersection points, if I pick any two Lagrange and that are two on -1 level. How do I see the data function? I agree the function of C is very periodic. But
Yeah, the theta function is, so not introduced this yet. So this is the sum over n in C, E, I, N, 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 That's
No, I mean, usually, right, the space of morphism is literally a collection of intersection points. In this case, there's no differential. So that's all it is.
yeah.
Do you
Oh,
function-
sorry. I know what I think I know what you're asking. Okay, so here this is K1 minus K2. Here it's X of L tensor K1, L tensor K2, which if K2 is greater than K1, this is Hom from LK1 to LK2, which is equivalent to H0 of the dual of the first one times the second one. So now we have sections of L to the K2 minus K1. And oh, and the next slide, I actually go more, I explain this a bit more. Yes. And there, yeah, quadratic term and then a linear term. Thank you. All right, so on the symplectic side, we have K2 minus K1. When K2 is bigger than K1, we'll call it those intersection points Pj. So the morphism in the Fukai category is C to the K2 minus K1. Sections of degree K2 minus K1 is also K2 minus K1. You expand with the Fourier expansion and you find a basis, and it's also K2 minus K1 sections of this here. Does that give a little bit more like motivation?
In the sense that I think of morphism as data function. Here, I should probably think of it as some kind of Fourier components of the data function. Is that?
I think.
How do you get it to depend on Z? How do you get something that depends on Z? I suppose. The way the data function, or Z and tau for that matter.
The tau shows up here. So this is actually, whoops, this is actually theta of 0, 0, tau Z.
You can think of this guy as an example of some X.
Yes, exactly. So the morphisms on the Fukaya side are the intersection points. The morphisms on DBCO are X'd.
Yeah.
And the A and the B here, if you have an A and a B, it goes into these two factors, which shift each of these. It adds shifts like N plus something, Z plus something.
Like, I think what she's saying is like you should think of the home space on the Fukai side as really the space of all the theta functions of a given level. And so like if you have like level K theta function, that just means like function on the pre-quotient with some automorphy the tau shifts. And then if you like write Fourier expansion for that function, the automorphy will use like the first K up to periodicity terms. So you can assign like one theta function to each intersection.
Yeah, you can think about a lattice. Like I think there's a way to think about this in terms of a lattice, and as you multiply by K in this 2 by 2 case, you're getting sorry, this is in the complex one-dimensional case. as you tensor L, your lattice is multiplying by K. But if we were in the, let's say we were looking at T4, complex dimension 2, then when you multiply, when you look at LK, your number of sections squares. So it would now be, so here, if this was a T4,
Yeah.
this would be K2 minus K1 squared. If this was a T6, it would be cubed, and so on. Yeah. Okay. Okay, so as vector spaces, these are the same dimension, but we also have composition in the category. Composition on the Fukaya side counts triangles. So you have two morphisms, you multiply them, your output should be a sum over intersection points. The coefficients on the output of a particular intersection point counts the number of triangles weighted by area between the three. I mentioned it was a Floer cohomology theory, so there is a differential which counts bigons. You have one intersection point, you take the differential, you count bigons to the other intersection point, but you can't have a bigon between two straight lines. They can't close back up, which you would see on the universal cover. So the differential is 0 here because we can't have a bigon between straight lines. The infinitely many triangles of increasing area in the universal cover of the T2 match the multiplication of theta functions. So the functor, Fukaya category to dB slope k with shift z maps to degree k with shift z. This pj maps to this sj, also respects composition. All right, so to say a little bit more about the J-holomorphic curve count, the differential counts bigons, one input and one output. Composition counts triangles, which is what this rest of the slide is about. 2 inputs and 1 output. The Fukaya category is actually A infinity category. So you also have maps with K inputs and 1 output where you count K plus 1 gons. And they satisfy A as associativity. So they satisfy relations like a Leibniz rule and D squared equals 0 and higher order operations. So looking at composition, composing from a map from L0 to L1, Lagrangian 0 to Lagrangian 1, Lagrangian 1 to Lagrangian 2, the output is from L0 to L2. L0 and L1, remember 1 minus 0 is 1, so there's only one intersection point there. Same for here. It's the same one, P and P. This one had the 2 intersection points, P and Q. So it was the one in the center and then the halfway one. So when we multiply, we have a sum over triangles between P, P, and P, and we have a sum over triangles between P, P, and Q. And they can be of increasing area. So we have all the homology classes that are getting larger and larger and the area of each of them. So this is an infinite series, this is an infinite series. What these are the counts of pseudo-holomorphic curves, D from the disk to a triangle on the 2 torus, so that the boundary of the disk goes to the 3 Lagrangians. And it's, remember, we always have a J. So it's holomorphic in the sense of the Cauchy-Riemann equations, it commutes with I, complex linear map, which we can say for the derivative of the map because we always have the J. So we say U is a J holomorphic curve. In particular, we get elliptic bootstrapping. So the moduli space of all of these, when you have a regular J, which you can show which we show in our work that you admit a regular J, you get that this is a smooth, compact zero-dimensional space, which you can count as a number. So for the same numbers, C1 and C2, if you work out this calculation, you get the coefficient on P and coefficient on Q. You get the same numbers when you multiply theta functions. So Mumford's book works out the formula for this, and it's the same number as the triangle count here. So that's Polishek-Zaslow in a nutshell, HMS for the elliptic curve. Any questions so far? Yes.
This case, is vibration trivial? That's for T2 or?
Yeah, so here it's a trivial vibration. That was here. This is the fiber, this is the base. So you just invert the fiber, keep the same base. If it did have singular fibers, you would only do that locally. and then how the additional disks that pass through the singularity would construct for you the transition maps between the charts.
Sure.
You're welcome. Okay, so here's a preview of our main result. We do homological mirror symmetry for the 2G torus, also known as an abelian variety, on the left side. In the top row of this diagram here is a complex geometry, dB-co of a 2G torus and the theta divisor, so a hypersurface of this theta function. This map is restriction to the hypersurface. Line bundles on the 2G torus restrict to line bundles on the hypersurface or theta divisor. In the bottom row, this is the symplectic side of mirror symmetry, where we get larger. You start out with a 2G torus, but that is actually a fiber. And so your slope K-Lagrangians, you parallel transport over a U shape in the base of a larger space. This is a symplectic fibration whose base is C. So you parallel transport around a U shape in the base of C. The way that our work fits into the literature is, it's first of all, one of the first results with a general type complex side. So this theta divisor is general type. Fano, which is when the first term class is positive, Calabi-Yau when the first term class is 0. Those have been studied, especially Calabi-Yau, that was the first case, the mirrors to those. Here, like for genus 2, C1 is less than 0. So that's new. And the Fukai category, this symplectic fibration is not exact. So the symplectic form doesn't give an exact cohomology class. And it's also not Lefschetz, which means maybe you've seen the picture where you have a cylinder and then it degenerates to the two cones. I think we were just talking about this earlier. That's a Lefschetz fibration. And these are generalizations of that higher dimensions. So we have to use U-shaped Lagrangians. Okay, so now let me break down all of this, all the parts in this. So the first thing that we have to do is globalize mirror symmetry for the torus, because what we saw was HMS for C mod a lattice, where the lattice was so 1 plus tau z, and tau was pure imaginary. But we want to be able to talk about any tau, not just the one parameter family of tau. So in order to do that, we need to do a process called globalization, looking at global mirror symmetry, which means allowing this tau to be any complex parameter. So we need to look at what are the complex structures on the two torus, and how do we mirror that on the other side. The next thing, this is what I mentioned before, compact Calabi-Yau, like tori, are mirrored to compact Calabi-Yau, mirrors to Fano, and mirrors to general type are Landau-Ginzburg models. These are non-compact complex manifolds Y with a holomorphic function V, which is the Landau-Ginzburg model part. And this holomorphic function helps govern the non-compactness of the complex manifold. So hypersurfaces of complex tori is an example of general type. I wanted to make a note about the use of the letter G. It's genus in the sense that a genus G curve embeds into a Jacobian torus, T2G. When G is equal to 2, genus 2 is a hypersurface in T4. But for higher G, this theta divisor is not the genus G curve, because genus G is always going to be complex one-dimensional, which wouldn't be a hypersurface in the 2G torus. So this theta divisor is complex codimension 1 in the 2G torus. Right. So what are the complex parameters on the torus? Now we're generalizing to the 2G torus. So CG mod ZG plus tau ZG. Complex structure is multiplication by the tau. Complex coordinates we can write as A plus tau B. And we do a coordinate switch where we take e to the 2 pi I z. So this goes away as a lattice. So now this is our abelian variety here. we want to be able to cut out a hypersurface. So we want this line, we want the abelian variety to be polarized, you know, like sunglasses are polarized to not let the sun in. We want to have the lattice polarized in a way that the abelian variety emits a line bundle, because then we can cut out the hypersurface from a section of that line bundle. So the hypersurface is cut out by section of a line bundle. We want tau such that tau ZG polarizes V tau to admit line bundles L. So here's our line bundle. It's a copy of C that respects this lattice action. And in other words, we need this, we need this to be a group action, this choice here on the C. And that turns out to be equivalent to the co-cycle condition for a line bundle. Here are the tau that do the job. They're complex valued. They're symmetric. The imaginary part is still positive definite. That's going to correspond to the symplectic area on the other side. These are the ones that polarize V tau to admit an ample line bundle. And it really is polarization with the lattice. H2 of Z and H11 has something. Those lattices line up so they have something. And that's the first Chern class of this ample line bundle. Okay, so we got this Siegel upper half space. Those are complex parameters. On the mirror side, we look at these T-dual fibrations. So we have our abelian variety V tau. We take the log norm of the coordinates here so that the angles give us the, so this is the T, this is the thing that we can take a T-dual of. This is the base of the fibration. This is the fiber, the tower, and the upper Siegel half space. Siegel upper half space. And we quotient by the subgroup of matrices that preserve this fiber and base splitting. So this C is 0, they preserve that fiber and base. The fiber is the H1 of TF. This is actually what you use to get the mirror, because you want the space of flat connections, so you want the holonomy around each of these loops. So you want this to be preserved. So this is going to characterize the moduli of symplectic structures on the mirror side. So our first result in our first paper is, okay, we have the theta function. It's this infinite series. It's a section of the ample line bundle. We have the theta divisor. That's the 0 set of the theta function. So for genus 2, when G is 2, the hypersurface is a genus 2 curve. And we have this SYZ mirror. So it's called generalized because it's not the mirror. The mirror to V tau is another 2G torus. Now we're talking about the mirror to the genus 2 curve. So you have to do a little bit more to get the mirror. So you have to generalize the SYZ construction because the hypersurface doesn't have the torus vibration. It's the abelian variety that does. This is the Kähler symplectic moduli of Y tau. And when G is equal to 2, we can actually draw what the symplectic and complex moduli look like. So V tau is abelian variety. We use a technology of Chan, Mello, and Viviani for tropical principally polarized abelian varieties for our result. This picture appears in their paper. They're talking about complex structures on abelian varieties on the complex side. And when we go through the symplectic moduli for the SYZ mirror, we can produce the same picture. We can write out the equations. They're linear equations, so we can solve them. And we actually can we get the exact same picture. So the cone decompositions, this is a different type of mirror symmetry than homological. It's mirror symmetry of the structures, the cone decomposition of the complex structures and the symplectic structures. So those are actually mirror to each other. So my thesis, actually, I did HMS for this one genus 2 curve right here. Okay.
Can you explain these sectors in the picture again?
So okay, this is we should think of this as a slice of a cone. So this is kind of coming out of the board and going into the board. This is a slice at height 1. And on the one hand, you can describe polarized, principally polarized abelian varieties, with these tau. earlier that I described, you can write down wall crossing as you vary the tau. You can write down a cone decomposition of the complex structures on the abelian variety and the genus 2 curves. So this is a Chan-Mello-Viviani paper. And you get this cone decomposition.
There's plenty too many concepts of which I don't understand the connection at this moment.
Yes.
So we do a cone decomposition of what? Space of is it a modular space of complex structures or a space of stability conditions, or what are we what's going on?
Let's see. So you need a variety of like pieces of information for the complex side. You need like a quadratic form, and you need like weighted graphs. There's like a whole machinery to build up how you describe the decomposition of complex structures on the genus 2 curve.
Yeah, in terms of discrete data.
In terms of discrete
exactly.
combinatorial data. And you get a cone, and the slice of that cone at height 1 is this picture.
Cone in what sense?
Like you have a parameter that is allowed to be in R plus. And so that parameter is equal to 1 in this picture.
It's general overall scaling.
Yeah, like an overall scaling, yeah.
Okay, oh, I see. And you just put that parameter to 1 and then you get this picture.
Yeah.
Okay.
On the symplectic side, you analyze these matrices, and they correspond to symplectic areas of P1s in your central fiber on the mirror. It only works in genus 2, because in order to do this on the symplectic side, you have to solve systems of equations. And if you get higher genus, you have to solve like cubic or degree 4, degree 5 higher polynomials, which you can't, there's not necessarily a way to do that. But on the symplectic side, when you write down the terms in your matrix, they correspond to area terms. And when you scale the values, you would pass into like negative areas. So you have this like wall crossing behavior where you have to do a transition to new chart, so your areas are still positive. And it produces the same picture when you do that.
Yeah. Okay.
That's very cool.
Thanks.
And then on the your mirror is always going to be a Landau-Ginzburg model for energy.
Yeah, it's always a Landau-Ginzburg model. Let me say more about the Landau-Ginzburg model now. Yeah.
Sorry, thank you for answering this question, but so just on the symplectic side, the various charts there correspond to what?
So they correspond to okay, so my thesis was for this matrix.
I can forget about the embedding of the preferred, can I? And just think about it abstractly, the class category of the two curve in this special.
Yeah, the main point of the embedding is like to get the line bundle. Once you have the line bundle and you've cut out the genus 2 curve by a section, I think you can forget about the embedding. So this is A1. It knows about the tau, and it knows about, so the mirror to the genus 2 curve is a degeneration of T4 to, well, this critical locus over 0 is the banana manifold. And the areas of each of these is A1, A2, A3, of each of these P1s.
Mm-hmm.
And this is there's also a description of the genus 2 curve with this kind of picture, but the constraints on the genus 2 curve is different because our constraints here, these have to be positive. And so my collaborator, Melissa, came up with a way coordinates to write these in, X, Y, and Z coordinates to write these in, and then linear equations between them. And when you draw out what they are, you get this picture. So this is the mirror Landau-Ginzburg model to the genus 2 curve. And the areas of those central P1s show up in this tau here. So my thesis, all of the A's had the same area. A1 equals A2 equals A3 equals 1. And I also didn't do, I mean, this global thing, I didn't think about.
And you probably have two-way mirror symmetry, right? You can also study the category that single guy, or that's not.
Yeah, Fukui category of the genus 2 curve, actually Seidel did that. So he has a mirror that he gets not by SYZ, but by a different way. And the thing in common with our mirror is this critical locus is the same in both. And Denis Roux and collaborators have a paper about trivalent graphs that talks about why this should be the same for any mirror. This as like thinking of it as a trivalent graph. So far, so good.
So,
Yeah.
the different charts on the category side, you must somehow be degenerating the genus 2 curve.
That's right. Yeah, when one of these parameters goes to 0. So our statement right now is about the cases where it's not degenerate. But you're right. That's crossing. Yeah, at a wall, one of these goes to 0. One of the areas goes to 0.
I see. And that's where something you just have because you could actually pinch. Okay, great.
Yeah,
Perfect.
yeah, that's when something gets pinched. Yeah.
Cool.
You do have Lagrangian thimbles that get pinched here already, even in this picture, which I have a slide later. All right, so we talked about how to build mirrors. We talked about the torus, we talked about hypersurfaces of the torus, and we talked about global mirror symmetry for those hypersurfaces, just on the structures. I'd like to say a word about DB-Co, what's going on there. What is the generalized SYZ mirror, and why is DB-Co compatible with it? So the SYZ input needed a Lagrangian torus vibration. The theta divisor doesn't have one. But if we cross the 2G torus with C and we blow up along the theta divisor, now the theta divisor is sitting as a critical locus inside the map, which is this projected to the C factor. So this thing does have a SYZ vibration. We call it Y tau. That's the generalized SYZ mirror of theta tau. Y tau is the SYZ mirror is defined by a moment polytope using the defining function of the hypersurface. So the thing where I said the T-dual and you do the charts locally and you glue them, the moment polytope encapsulates that. The vertices are the charts, the edges give you the gluing, and once you have a moment polytope, you have a symplectic form and you have your full symplectic manifold. So why was this okay to do on the complex side? Well, why should X tau give us the same invariance as theta tau? That's really what we wanted the mirror to. So there's this classical relation between DB-Co of the blowup and DB-Co of the theta divisor, which is a semi-orthogonal decomposition. So there's morphisms in one direction, but not in the other. It's like how O of 1 has sections on P2, but O of -1 does not. So we're all good. Inside of DB-Co of X is the thing that we want, which is DB-Co of theta. there's a new feature. So remember I talked about this was purely imaginary, and we had to have the space of flat connections. When we add in a real part here, there's two things that need to adapt. The symplectic form needs to match it. So like in the previous picture, the P1s, there were 3 parameters, but the space of complex structures on the genus 2 curve is 6-dimensional. So we need to complexify the symplectic form to have like symplectic complexified the 3 P1s so that we have 6 total. So now the symplectic form will have will be complexified, and instead of flat connections on your Lagrangians, they now have curvature B. So this is, when you globalize, you need to add in a B field, is the point here. Okay, so a word about this moment polytope. A moment polytope defines a toric symplectic manifold via symplectic reduction. When we do that process, we obtain a family of complex G+1 folds y tau parametrized by a moment polytope that depends only on the imaginary part. And the symplectic form, you also get that as part of symplectic reduction. So we adapt a form from Cannizzo Liu, who have a symplectic form by symplectic reduction. And we complexify the symplectic form. So we add in this B field, which is a cohomology, which is a 2 form that's closed. When G equals 2, here's what the mirror looks like. A generic fiber is a T4. Inside of the T4, we have slope K Lagrangians again. So we can still talk about linear Lagrangians. The last 2 coordinates are K times the first 2 coordinates. We still have triangles. In the base, we have these U shapes. And your input Lagrangian, the ends of the input Lagrangian have to lie above the ends of the output Lagrangian. If they don't, you have to push the ends so that they do. And the critical locus here over 0 looks like this banana manifold. So 3 P1s over 0. So T4 fiber degenerates. The critical locus of the degenerated fiber is the banana manifold. That's the mirror to the genus 2 curve. And the this is a product of the toric coordinates on here.
So why is mirror to all of X, right?
Y is mirror to all of X. So there's different. So theta.
Maybe not all the critical.
Yeah, really the critical locus. You can kind of think of, if you like, you can kind of think of this as the mirror, because it kind of looks like a genus 2 curve. And it's the right dimension too. This is too big of a dimension.
That's
So
going to be the right part of the category. Whatever fiber.
well, so we actually avoid the singular fiber because it would be too singular to pass through it. And so it's monodromy around this that's going to give us all the calculations.
How do you use the B field?
The B field is used to, so here, the genus 2 curve, when G equals 2, we get the genus 2 curve. This has 6 real parameters for the complex structure of the tau, this symmetry, but this one only has 3.
On the A side, where does the B field into the calculation part of the problem? What does it?
Oh, it's right here. So it's when you write your tau, you can write your tau as B plus I omega. And this is only captured by this A1, A2, A3. So you need your symplectic form on Y tau, you need, sorry, we actually, our notation now is this. I didn't update it yet.
You want to not zero, I mean, you want to simplify the length of the 0 to 0 or not.
So the objects, I will have a slide. Next slide. Oh yeah, it's right here. Okay. So Okay, just a note about this. When I teach, I do this is a technique I learned. I do 4 perspectives: verbal, symbolic, visual, and numeric. So I do that here. The numeric is the next slide. So verbally, for HMS for theta tau, this is a description of the Fukai category. So the verbal description of the Lagrangians are, you have your 4 torus as a generic fiber. You take slope k Lagrangians, and you take the fiber over -1, so slope k over -1, and you have a symplectic form. So that means you have parallel transport. You parallel transport them over a U shape. That gives you your Lagrangians in the total space. They also have to have a connection 1 form, but now the connection 1 form has to have curvature equal to this B. Sorry, this should be. B is a 2 form, so this should be, sorry, B is a matrix, and this is the symplectic part, the 2 form. Okay, symbolically, so we have the LKB, K is the slope in the fiber, B is the shift in the fiber. A is over here, it is, if you restrict to a fiber, it's a flat connection. And so this A is the ADR that we had before. And so you want in a fiber, it's going to be flat. Restricted to the fiber, it's going to be 0. In the total space, you're going to get that the curvature is this omega B.
The total curvature is actually B plus the curvature of the line.
Yeah.
So you want that total curvature there. Then 1 plus.
So this is the curvature in the total space. So your omega B is omega B is something defined on all of Y tau. You restrict it to your Lagrangian. Yeah, it's part of the symplectic form. And it's mirrored to the B field. I mean, it is the B field. It's mirrored to the B that was the real part of the tau describing the complex structures. So the V naught of L in the base is a U shape around 0. And the curvature of this connection is -2 pi I times the B field when you restrict it to the Lagrangian. This is only defined on the Lagrangian. This is defined on the whole space, so we restrict it to the Lagrangian. And the visual is this picture. So when you have 2 U shapes and you perturb them into correct position, you have 2 intersection points in the base. So you have intersection points in 2 fibers. This fiber, when you parallel transport in this amount and this amount, you can do some calculations and say, actually, this is the same as intersection points between K1 plus 1. You add 1 to the slope. So this is K1 plus 1, K2, and this is K1, K2. And these we actually know how everything works by HMS for the torus. Okay, so this completes the description of the Lagrangians in the Fukaya category of the mirror. Then the question is, what is the differential? The differential was 0 for the torus. It's definitely not 0 in the total space because you have this bicon right here. So what we do in order to, yeah.
The K1, K2 like
Slope.
slope and twofold, right?
It's actually an integer.
Integer.
Yeah, it's still because if we really want to get symbolic, L, K, B is the set of all.
B2 or B.
In case so the slope is 1 comma k.
Okay.
That's the direct direction.
Yeah, so this is J equals 1 up to G. So K is still an integer. K is still, it's the same slope K in each coordinate. But B is now, there's G of them. A and B are now in RG. So to compute this differential, that's really the crux of the calculation, is computing this differential. And
No, I don't understand.
Yeah.
Alpha and beta are coordinates where? On the big torus? Before you restrict to the. Sorry.
R's and thetas,
Before you restrict to the theta plot.
so we had this v tau, and inside of it we had the theta divisor. And then we had a mirror T2G, which is a fiber of the y tau. So the SYZ happens on these. They have the same base and they have dual fibers. This is the same base, and this is the fiber that's dual to this one.
May I ask where
Yes.
the equivalence of the flare complex, for instance, transport, does the V2 still appear on the right-hand side? I don't see it in the public eye.
You're so observant. As I was saying it, I realized I had dropped it, and I was hoping that would call me out.
Oh, I see. So if you do want. You're deciding to pack it as one.
I forgot. I dropped it. Yeah.
Mhm.
Good catch.
The polarity, the critical loci of these variables,
Right here.
the leading over time. So what does it look like?
It's so. I don't know if I can add a page.
You showed it for Chiu-Chu, that's that thing, but.
So when G equals 2, T4 degenerates to CP2 blown up at 3 points modulo the gamma tau. And sitting inside of this is the critical locus of V0, which is the 3 P1s, yeah. So in general G, you have a T2G degenerating to, that's like an open question. I mean, you can write down the polytope. So if G is equal to 1, the polytope looks like this. And modulo a lattice. And this is going to lead to a string of P1s, which is going to lead to a central fiber of this. When G is equal to 2, you actually get a bowl that's tiled by hexagons. And you take everything above that. And this, the critical locus, which is this point here, is this after the lattice. So you identify opposite sides of the hexagon, you get 3 P1s. But in general, it's hard to describe it.
The G. Heading of the G and the quotient recipe.
Yeah, like the reason we know this is a picture is coming from the theta function. You like tropicalize the theta function, you look at a periodicity property, and you write down equations that allow you to write this down. In higher dimensions, it's harder to do that. Yes, somehow we are able to count the disk. This is how we count the disk. So right now, this is really ad hoc. We have a slope K Lagrangian parallel transported here, another one here. We want to count disks over this. What we do know is if you take the vertical Lagrangian and you parallel transport that in a circle around the origin, that's something that we know how to count, actually. So what we do is we introduce this L infinity, which is the vertical Lagrangian around a U shape. We look at disks, the moduli space of disks of index 1 bounded by the 3 Lagrangians in the total space. That's compactified is a one-dimensional manifold whose signed count of its boundary is 0. That's how you prove the Leibniz rule in a Fukaya category.
What's the specialty about the vertical?
Because we know how to count disks bounded by them.
What does it look like?
It's in a fiber, it's the vertical Lagrangian, and then it's parallel transport around a U shape. It's this one, the infinite slope.
Oh, that.
This one. Yeah. So there's this B.
They're not fiber in the base.
Yeah.
So what's the increase that for?
You increase the slope by 1. But this one, it preserves it. That's the thing. With the L infinity, it's infinity. So Daintus preserves it. It preserves the slope. And yeah, makes me happy too. It's a pre-image of a moment map, actually. If you have the moment polytope and you look at a pre-image of a point, that's your Lagrangian boundary condition. It's actually a fiber of the Lagrangian torus fibration. You know, there's 2 fibrations. There's the Landau-Ginzburg model, and there's the Lagrangian torus fibration that you do SYZ to. And this L infinity around a circle is a Lagrangian torus fiber. And disks bounded by that, Cho and O have a very nice formula.
Yes.
Yeah. So. Yeah. It's a product of the toric coordinates, so that your toric divisors are happening over 0. All right, so this, oh yeah. Okay, so the point is, if you count disks in this moduli space, and you count disks in this moduli space, the 2 counts are equal because they're the boundary configurations of a one-dimensional moduli space whose the boundary count, signed boundary count is 0. And this is something we know how to count. This is something that we can deform to figure out how to count. This is triangle count in a fiber, which we did at the beginning. And this is the differential that we want. So essentially we solve an equation for the differential which we want to do. Yeah, so there's degenerations of a disk with 3 points as two of the points come together. So this is one possible thing that can happen. You have triangles. So do I have?
Understand why you have a bicon counting the
If you introduce a third Lagrangian here, there's an intersection point here, which I call mid. There's an intersection point here, which I call right 1. There's an intersection point here, which I call right 2. And then there's this one, which is left. So this is when you introduce a third Lagrangian, this is the L infinity will be introduced here. Then you look at the moduli space of disks bounded by those 3, index 1, and you look at the degenerations. One of the degenerations when 2 of those points come together is this. So you have a bigone between the left and the mid.
Is the picture of this degeneration, or is it about the face of the aberration?
This is the total space, actually. Like, for example, this is in a fiber. This is a bigone covering left and mid. This is a triangle covering left, mid, and right 1. These are the same point in the base, but they're different points in the fiber over mid. And this is a triangle that doesn't include the fiber over 0. And so we wrote a paper about how to track the area changes in that case.
So what you draw on the right side, is the boundary point of the one dimensional?
Yeah, so this is like, let's see, we have a count of these disks. This is L infinity, this is LK1, this is LK2. U equals this disk, such that the index of U is 1. And then we compactify. So this is now a compact one-dimensional manifold. So it's collections of things like this and things like this. In particular, the boundary, the signed count of the boundary of each of these is 0. Because this is like plus and minus, and this one doesn't have a boundary. So if we take the boundary of this, we get 0. But what this means geometrically is how can the disk degenerate? So if you have a triangle, you can strip break here, here, or here. So what that means is when you strip break, you break off a strip. I say strip because this is biholomorphic to this. So there's 3, and then you have another configuration doing that here and here. One of those ends up being 0. There's no configurations, but the other 2 produce these 2 pictures. It's like a calculation that we do, that it works out to be these particular triangles.
Okay, thank you.
Yeah. So let's see here. So the main idea is, one thing that's that we do is we incorporate this B field, which not a lot of people do, because we want to do this global mirror symmetry result. We want to talk about, we do global mirror symmetry in genus 2, and we pick an arbitrary symplectic form, including a B field in higher genus. A big calculation is that of the differential, because we're trying to show that HOMs on the complex side, the X groups of Lagrangian, of line bundles restricted to the theta divisor, equal HOMs on the Fukai category side, which means we need to compute this bygone. So in order to do that, we can count J-holomorphic triangles in a fiber, that's this one. We can count disks bounded by L infinity over a circle around 0, which we do see this top. Here the top Lagrangian is LK2. Here the top Lagrangian is L infinity. So we can deform this Lagrangian until it's a disk around, until it's a curve around 0. And then that's something that we can finally count. And we just keep track of how the area changes otherwise. There's also sphere bubbles here, but Cannizzo have figured out what those are. Our setting is not exact, so we must also keep track of areas of disks when isotoping Lagrangians to these 2 cases, which we have a couple of papers where we talk about how to do that. Okay. And so note on Lagrangian brains.
Sure. Well, especially something like Lagrangian in the middle picture,
In this one, yeah, we isotope. In order to count this bygone, we actually do yet one additional thing. This is Seidel's book on Fukai categories of Leschetz vibrations, where he has all these homotopies. We use that. So we vary this Lagrangian until it bubbles off a disk in the base. So we get a cobordism of moduli spaces. So like zooming in this.
I thought you fix the Lagrangian and just have a one-dimensional moduli space of this and look at in 2 ways like degeneration.
That's the first step. And then we move the Lagrangians again. So first we degenerate the disks to these two, and then we produce a cobordism of moduli spaces. So here, your Lagrangians are fixed. Here, the second step, the Seidel homotopy, they're not. You have a family of choices of Lagrangians. And so you produce a cobordism with that family.
Why don't you by counting triangle and it's generating a corner?
Yeah, we want to count. We want to count. The goal is to count this, and then we just have some kind of ad hoc methods to count everything else. Like either splitting pictures into like base and fiber pictures where we compute the area of a fiber and area base, or moving, like changing our Lagrangians and almost complex structures to ones that we want, and then showing there's like cobordism between the two choices.
So this follows from some infinity relations for like Foucault category that
This picture here, that's Foucault category relations for fixing the y tau, like for a fixed thing. Then Seidel has this parametrized moduli spaces where you vary your choices of Lagrangian, and then that's like a family version. You have a family of moduli spaces where you change your choices of Lagrangian.
a little too technical, so we can
It's
explain to us.
Yeah, sorry, yeah, that's kind of technical. Okay, so I also did my PhD here. I graduated in 2019. Everybody was always talking about Aganaga-Chvafa rings, and so I was so honored that you asked me to speak in the seminar. I wanted to make a note, which is our Lagrangians avoid the singular fiber. Usually you have thimbles that go straight to your singular fiber. You can do that when G is 1. So the mirror, when G is 1, if you think about it as a hypersurface and an elliptic curve, the mirror is a Tate curve. You have a T2 degenerating to a pinch T2. And in that case, if you take a fiber, it's a S1. And so you can just degenerate it to 0. You have something one-dimensional going to something 0-dimensional. The whole thing is smooth. But in higher dimensions, you'd have a T2 or a T3 or a T4 in your fiber Lagrangian all going down by a codimension bigger than 1 over 0. So that's why we do the U shape around it instead of to it. So, but I'm curious to know more about the famous Aganaga-Chvafa brains, because my understanding is when you have like a product of 3, like Y1, Y2, Y3 equals 0, it's the brain that goes directly to the central fiber, I think. Like you have the 3, if you just have Y1 times Y2 equals 0, you have your fiber over 0 is like the one cone and then the other cone. And the brains, I think you have 3 of them from the 3 being 0. So I'm interested in thinking about what if your Lagrangians do go right to the central fiber. Yeah. So I'll just conclude on this slide that we already saw before. So yes.
TG is a Lagrangian.
Yeah, because you have a T2G fiber, so the Lagrangian is TG. It's the slope K1. It's this one.
Collapsing which guy too?
This would get collapsed to a point. All of them, all the Lagrangians would collapse to the critical point here. So like here, you'd have a T2 and it would collapse to a point here.
Which T?
This one, when G is equal to 2.
So there,
I know something about it. I thought the banana picture is in fiber. So I misunderstood it completely.
It is in a fiber.
it's in the singular fact, it's part of the rule file.
Because it,
So the banana picture I get in over the point, the black one, right?
Yeah.
because a thimble normally, okay, if G is equal to 1, this is the mirror. And you would have, I think this one. Or is it the other one? Oh, that one, okay. This one would go to this point.
Yeah.
Yeah, which is a smooth submanifold. But if you're in higher dimensions, so T4, then you'd have a T2 inside of that going to so you have dimension T2 going to dimension 0. And it wouldn't be a manifold then, because it's singular. Like this one?
I don't know, like the usual slogan is like one field in a singular low side. And if you think of it as singular low side and not a zero dimension. So I wouldn't expect it collapse to a point. That's the Lagrangian in particular. It's like the tip of the generalized symbol is another Lagrangian.
I have to think more about it. Okay. But you're saying it doesn't have to collapse all the way down to a point.
Or, I guess, or maybe for some special choice of Lagrangian. There are Lagrangian people that collapse to a point.
Okay.
Just like in the lot of Ginsburg model. Really.
Yeah.
But that the banana is complex, right? It's a luminously complex P1.
Yeah.
I mean,
So I think
that's like one example of that. The tip of the generalized symbol is just S1. And drag out
Exactly.
the thing. So the tip of the symbol, generalized symbol, should be a point. It should be
An S1.
in
Oh.
S1. So that one is
So then you'd have,
Yeah.
so then they would intersect, multiple Lagrangians would intersect there.
no, but the problem is, okay. So what you have to understand the crack of that the general guy, right? Because the circle guy looks like it wants to shrink to the single point. It's possible there's something stabilized and it doesn't.
Yeah, I don't know how.
Like on a P1, there's a potential that makes you actually stay. I don't know.
Oh, okay. Oh, so it depends on the potential. To be continued. So yeah, that's the end of my talk. This is just the same slide I had earlier. So HMS, oh, now it works. Okay. For the torus, restrict to the hypersurface parallel transport from the torus fiber. And HOMS, that the HOMS in these are isomorphic as our result. And thank you for your time.
So, all these measures fit into the bigger picture, I think, sketched by Bridgeland 2006 or something. Stability conditions and deformations in mirror to each other, right? Can you elaborate a bit on that?
You should ask my collaborator Heather Lee, because she wrote a paper about that.
Yeah. What I've seen here is, what I've seen in their talk is, that only after adding this visual parameter, you actually can pass from a symplectic structure